So let's look at bonding. And as we look at bonding, we have to figure out the number of bonds of each non-metal. Because if we remember that throughout the semester, we'll be able to see why certain elements and certain atoms exchange electrons or gain or lose electrons and form double or single bonds within enzymatic reactions and different types of transformations. So if we look at the atoms, we're going to mainly consider, we're going to look at carbon, we're going to look at hydrogen, we're going to look at oxygen, sulfur, phosphorus, nitrogen, fluorine, chlorine, bromine, iodine. These are our main elements that we're going to look at. And in terms of the number, so let's look at the number of valence electrons. The number of valence electrons within each atom. Carbon's got 4, hydrogen's got 1, oxygen and sulfur obviously have 6 because they're in the same family. Phosphorus and nitrogen have the same because they're in the same family. And then fluorine, chlorine, bromine, iodine, those are halogens. So we've got that. And then we want to know, obviously we want 8 valence electrons. So how many electrons do we want to gain? So we need 4 here. We need 1 here because remember hydrogen is going to be the same as helium. We've got 2, so we need, we've got 6, so we need 2. Sulfur's got 6 valence electrons, we need 2 more. We need 3 more here, and then obviously the halogens all need 1 more valence electron. So 7 plus 1 gives us 8, 5 plus 3 gives us 8, 6 plus 2 gives us 8, 4 plus 4 gives us 8. So if we look at this number, we can see that carbon, in terms of the number of bonds, carbon will form 4 bonds, hydrogen will form 1 bond. When we look up these 4 bonds, remember we can have singles, doubles, or triple bonds. Oxygen's going to form 2 bonds. Sulfur's going to form 2 bonds, but we also want to remember that it's got 4 or 6, and we'll talk about that in a second. Phosphorus has 3. We can also form 3 or 5, and nitrogen can form 3. So you can see that the green and red numbers are the same. Just want to mention the fact that sulfur and phosphorus are in a lower row in the periodic table. Because of that, they have access to the d orbitals, and having access to the d orbitals means that they can hybridize further, and if they hybridize further, they can accept electrons. Remember, orbitals want electrons, so by accepting electrons, they can form 5 or 4 or 6 bonds respectively. And then finally, the halogens all form 1 bond. So when you're drawing out your structures, you always want to remember that's the number of bonds they're going to form. That's important. So if we look at a chemical formula, C4H9BrNO3, this is a chemical formula, and with all of our chemical formulas, it's carbon, hydrogen, and then everything else is in alphabetical order: bromine, nitrogen, oxygen, BrNO. And if we look at a molecule of this type, I'll try to draw this out. We've got HOC, HHC, double bond O, C, Br, H, C, O, H, H, N, H, and H. If we look closely, every hydrogen has 1 bond, every nitrogen has 3 bonds, every oxygen has 2 bonds. Apologize, that should be 8, sorry. So that's our chemical structure. So this is an example of a chemical structure. And if we look closely, we can say, oh wait, this bond is polar, because bromine's more electronegative than carbon, oxygen's more electronegative than carbon, oxygen's more electronegative than hydrogen. So not only can we identify the bonds, we can identify which are polar and which are non-polar. Okay, so these are all polar covalent bonds. So as you're drawing your chemical structures and carrying out your enzymatic reactions, within your biology classes and courses, you want to consistently remember that there are polar bonds. We have to think about a chemical formula and chemical structure and make sure each atom has the right number of bonds. So it's just a constant counting. And so another way to look at this chemical structure is in a line bond form, which is what we're going to consistently see most of the time. And so this would look like this, okay, in which every line represents bonds between carbons, and lines between carbons and non-carbon atoms represent other bonds. And then you can see that hydrogens attached to non-carbon atoms are shown, but the hydrogens attached to carbons are not shown. So that's going to be important as you look at different texts and different journals and you Google things to recognize that.